So we are looking at the revision package for question paper for August 2022. That's for Diploma in Automotive Engineering Level 2, subject Mechanics of Machines. Now, as the tradition, this is meant to just see or to gauge your preparedness in this subject. So for each of the questions, you'll see definitions and then the calculations that follow. Now here, I'll try to pick up the first four, and then the last recording that will follow part 2, I'll also pick up the other 4 questions. So traditionally, let me start with question number 1. So in question number 1, I have, this question was saying distinguish between kinetic energy, or rather distinguish kinetic energy from potential energy. So what is the difference between KE and PE? That's what it is saying. Now, traditionally, when you look at the two, the main difference is the fact that one of them deals with motion, the other one doesn't. But whenever you're differentiating or trying to distinguish, the best way to do it is to define them in full. Here we're saying that kinetic energy, that's the kind of energy a body may possess once in motion, or a body in motion possesses. But as for potential, it's that kind of energy which a body possesses due to its height above a given surface. Then the other one, of course, to make it complete, you also add the formulas. Now the formulas, please don't misuse them. Those formulas are meant to support what you're writing. When they say distinguish, you don't just go and step the formula and you move away. No, you just have to put them there so that after you define, that's when you can plug them there. Principle of conservation of energy. Here we're saying that you can neither destroy nor create energy. But what happens? That energy has to be transformed from one form to the other. So the question that we had in part C is that we have a mass, the mass of the stone, 0.5 ton, and it falls through to a pile without rebounding. So it has fallen through a vertical height of 200 millimeters into, rather penetrating into the ground through a vertical height of 200 millimeters. Meaning it drives the pile straight into the ground through 200 millimeters. Now, here, the one thing I think that I didn't just copy out in the question is that it falls, a stone of mass 0.5 ton falls from raised to a pile of mass 144 kg through, this is through a vertical height of, so according to that question, the height that we had been given was 8.1 meters. So the condition is that it doesn't rebound. And then part 1 is asking for the striking velocity of the stone, the common velocity of the stone and the pile, and lastly, average resisting force on the ground. So let's pick up the information provided in this question. First, it's the mass of the stone. 1 ton represents 1,000 kg. So we say 0.5 ton, which is the mass of the stone. Of course, not a ton, but this, yes, okay, it's fine there. 0.5, then you multiply it by 1,000. The answer gives us the same 500 kg. The SI unit for mass maintained, that's 500 kg. Then after that, you have a vertical height, 8.1 meters. The mass number 2. This is the mass of the load where the stone is hammering, and this is the pile. And this is given as 144 kg. Then by how much does it penetrate into the ground? We're calling it Y, and it's 200 millimeters. Again, we convert the height to the SI unit. So you divide that 200 by 1,000 for us to get that one. So 200 divided by 1,000, we have 0.2 meters. Away from there, we are now trying to find what is the striking velocity. With what velocity is this stone going to hit the pile. We go back to the principle of conservation of energy, where we are saying potential energy that is going to be lost will be equal to the kinetic energy that will be gained. So hence, this equation here, potential energy is equal to kinetic energy. Replacing back the formulas for potential energy, we have mgh. For kinetic energy is half mv squared. And this is where this popular formula comes from. That is V given by root of 2gh. So 2gh. And we just do the substitution. 2 is there. G is 9.81. H, which is the height, is actually 8.1 meters. Having found the answer, you find 2 by 9.81 by 8.1. Whatever you get from there, get the square root. So what it was giving here was 12.606 meters per second. This is straight away talking about the velocity with which it's going to hit the ground. Now, when you make a step further, the next one is now asking the velocity of the stone and pile together. How? So here, the velocity of the stone and pile is referring to after they collide. We're given a condition that after the stone hits on the pile, they move together. It doesn't rebound, referring to the fact that this is an inelastic collision. And it means, to avoid confusion, we also have to write the data for this. Meaning, here is our mass of the stone, mass 1, 500 kg, mass of the pile, mass 2, is 400 kg. Now, with this, when you move further, you find that the initial velocity of the stone, with rather the velocity with which the stone hit the pile, it is 12.606 meters per second. At what velocity was the pile moving at that time, just before it was hit by this stone? It was stationary, meaning the velocity was 0. Now, the two of them are going to have a common velocity. So to get that, we'll avoid making assumptions. So we're going to consider V to be unknown, and hence our question mark for V, the common velocity. Let's go back to this is where the data ends. So hence our solution. Now here in our solution, we are looking at the expression for the inelastic collision. An inelastic collision is where, let me just zoom out a bit, zoom in a bit. In an inelastic collision, you have the two momentums, the initial and the final, summation. You add them together and you equate it to the final momentum. In the final momentum, because they'll have one velocity which is common, so you add the two, m1 by m2, or rather m1 plus m2. Then outside the brackets, you have the velocity v. You're going to have that velocity v just like that. Now here, okay, just a quick minute, I just put a v out there. So m1, m2, then velocity. And that is our common velocity. Now, here, let's proceed to do the substitution. Mass number 1, let me go back and check. What did we have for mass number 1? It's half a ton. So that's 500 kg. So that's 500 kg multiplied by initial velocity of mass 1, which is 12.606 before the collision. Add this to mass number 2, which is 144 kg, by 0. Then all this is equal to, then we add the two masses, 500 plus 144, then common velocity stands out. Then what do we do after that? We can now just do the algebra. When you multiply 500 by 12.606, it gives you 6,303. Then you're adding to 0. End result is 644 V. So now that we have 644, we divide through by 644. So that's where we have 6303 divided by 644. And there it is, the answer that we should be getting, the answer that we are getting is 9.787 meters per second. 9.787 meters per second. So that is our common velocity, rather the velocity with which that combination enters the ground, or rather moves together as one unit. Now, after that, we were given another condition that the ground had to resist. It only penetrated into the ground by 200 millimeters. Now, how much resisting force did we get as a result of that penetration into the ground? So again, we revisit the principle of conservation of this energy. We're saying, how much potential energy are we going to lose? And what will be the work done in resisting the penetration into the ground? So what we have here is that the total potential energy that will be lost should be equal to the work done by the ground in resisting all that. So this total potential energy will be, first, the potential energy as a result of the first mass, which went through the total height 8.1 and the one into the ground. Then with mass 2, it only penetrated through that small height, which is y. And it's supposed to be equal to the product of force multiplied by y. In other words, this is the formula for work done, force times distance. Then from there, now we can just do the substitution. We have 500 by 9.81 is equal to 8.1 plus 0.2. Then the result should be now the whole of this. And I want to make sure that we put all of this in brackets. So I'll just cage it again. So 144 by 9.81 multiplied by 0.2. Then all this is equal to F multiplied by the same 0.2 that we have there. And here again, let me just cage this family here. This one, just give it another set of brackets to make it look unique so we don't mix them up. So from here, all this is now, when you enter those values, try to simplify them. You just end up with one number for the first part, which is 40,711.5 added to 282.528. On the right-hand side is just 0.2 F. The result of this is now requiring us to divide through by that 0.2 so that you just make F the subject of the formula because we're looking for the force. And the answer comes out as 20.5, or rather 204,970.14. So that is our resisting force coming from there. If you want, you can call it R. Pick up question number 2. In question number 2 is talking about the disadvantages and advantages of friction. Here you can feel free to maneuver. Friction has so many applications. That is where advantages come in. It has so many problems that come from it. For example, useful heat is generated from there. If you talk about lighters that we use in the workshop, they use friction. Motion transmission in the belts, in the transmissions there, the clutches, especially the friction clutches, they all rely on friction. Talk about the brakes, even traction control on our vehicles, it's all about the same friction. When you talk about the disadvantages, you're talking about things like the famous wear and tear, reducing the efficiency, noise pollution, as well as generating unwanted heat or excessive heat in bearings and other sensitive components. Now, once again, here we're saying that you are free to pick any two. Next, Here is our question. It says a box having a mass of 1 ton is pulled up a track inclined at 30 degrees to and above the horizontal by a force of 6230 inclined at 20 degrees to and above the track. Calculate the coefficient of friction between the box and the track. Again, we'll start with the data. First, we have the mass, which is 1 ton, converted to kilograms. So here it's 1 by 1,000. 1 by 1,000, then you get 1,000. And we want the weight from there, so we say 1,000 multiplied by 9.81. It gives us 9,810. Then proceed from there, we have the angle, which is theta. The angle of inclination of the track or the plane where this body is resting. This is 30 degrees. Now, this is a question which you do not just work around by barely looking at the figures and then perhaps you pick one standard formula just like that. Yes, there are instances where we're able to do that, but we encourage you to come up with a diagram so that you can clearly identify and account for each of the forces and what you end up with. So here I have it. The question is saying that this body we are pulling is resting on a track whose angle of inclination is 30 degrees to and above the horizontal, whereas the force is inclined at 20 degrees above the track. Let's put the two together. This is the 30 degrees to the horizontal. And because this thing here, the blue line here is representing the track, the angle between that blue line and my force, which is 6230, is 20 degrees. Hence, the angle of inclination of the force above the track, right there, 20 degrees being measured above, not below. You can also have a case where this force is acting horizontally, meaning it follows the x-axis, stemming from there, going straight into that other side, and you resolve once again. So here we are. We require to resolve these two. So if you look at 6230, it has two components. This one, which is more like an inverted vertical. The other one, also an inverted horizontal. The two components are meeting at 90 degrees. So that's why you have 6230 cos 20. 6230 cos 20 is representing the horizontal axis. You can always prove this by going back to looking at this box, applying SOHCAHTOA, and making this be represented by just any other letter like Y or X. Make it a subject, then this is what you have. You do the same on the other end. Then when it comes to now the weight is very stubborn. It always acts vertically, whether you're rotating or whether or perhaps it's at an angle. It will always act like that in the y-axis. So with that, that's why now we also need the two components. There's this component and the other component. And aside from that, we have the normal, which is basically at 90 degrees to the plane or to the surface. So the 9810, which is the weight, we also resolve it in the two. The 30 degrees that we are seeing right here is actually the angle of inclination for this, the angle inside this box. That's the angle we have. And hence, we have 9810 cos 30 and 9810 sin 30. Wow, this is our 9810 as our weight. Now, here's where you need to be very careful. When you're resolving these forces, this is where you have to be very careful, because if you get this part wrong, it means where you are going, you also get all of them wrong. So the first thing you need to do is to resolve along or parallel to the plane. We're talking about forces acting just along there. If you check parallel or along the plane, the first one I can see is 9810 sin 30. There's also 6230 cos 20. And there's also mu n, which is the friction force. 1, 2, and 3. Anything more? I think that is the end. Now check the arrows where they are pointing. Here, this friction force, mu n, according to the rules, friction will always oppose motion. And that's why, as you can see, it is pointing down the plane, whereas we're trying to pull this thing up. Now, the first one, which is 98 10 sine 30, and mu n, they're acting in the same direction. So then the other one is in the opposite direction. So all we do now is just add the two. This added to that. This is the first equation you're seeing here. We have 98 10 sine 30 added to mu n is equal to the other one acting in the opposite direction, which is 62 30 cos 20. And hence we have this first equation. What I usually encourage is that you don't even disturb that one. You leave it as it is. Then from there, you proceed now to the second equation. In the second equation, you have n, which is at 90 degrees. So n, the other forces which are acting like that or in that same direction, we also have 98 10 cos 30. We also have 62 30 sine 20. So I have 1, 2, and 3. Again, let's check out the arrows. The first arrow is pointing upwards. The second arrow is also pointing above the plane, up. The last one is going down the plane. Down the plane, which means it's now in the opposite direction to the first two. Now, what do? The two that are pointing in the same direction, we should add them, equals forces in the opposite direction. Just as simple as that. So we will say n plus 62 30 sine 20 equals, or we equate now, and on the other side we have 98 10 cos 30. That completes our setup, and hence here we are. N plus 62 30 sine 20 equals 98 10 cos 30. So this is supposed to be our second equation, but we can do better than that. Let's make n the subject of the formula. By making n the subject of your formula, you get this part to the other side, which requires that now we subtract. So then we have 98 10 cos 30, take away 62 30 sine 20. From there, you end up with 6,364.924. Now, this has given us the first equation. The second equation, where we've already resolved, we've already found the value for n. So this we can now replace in this other equation here, because according to the question, our target is just this. We just want to find coefficient of friction. And hence, when you do that, where there was mu, you substitute 6364.924. The other one remains the way it was, and the other side, it remains intact. So your mu will be 0.149, which is almost like 0.15. That is how you handle that part of the question. Now, my caution is, please do not rush to this question to start solving before you do a good job with a good free body diagram that will show you how things are happening, or rather, a good diagram that represents all the forces, and then you proceed from there. And you have a number of options. Sometimes you connect the free body diagram with the three main forces and come up with a triangle of forces, or rather, a system of forces that will help you to resolve what you want. But basically, this makes your work much easier. Let's pick up another one. Here's question 3. Definition: out of balance force, then dynamic balance. Well, an out of balance force is that force which is able to cause vibrations because it's not balanced. A system has ended up with some imbalance because of that same out of balance force. So that's what it is. And out of that one, when you talk about force that could be coming from a system, it's because of the same out of balance force, which may require to be sorted out. When you resolve, then you know how much mass you need to put there for the system to balance. Now here we had a question, and in this question we're given 3 masses. Mass 1 was 5 kg, mass 2 was 7 kg, mass 3 was 12 kg. Now from the 3 masses, the radii, or each one radius from the center, or the radial distance from the center of rotation, the axis of rotation. The first one was 120 millimeters, which is 0.12. The second one was 105 millimeters, 0.105. And the last one, third, was 75 millimeters. When you convert it, becomes 0.075 meters. The angles were 0, 70, and 130. Now, the way the question was phrased was that the angles given were only for B and C, measured from A. B was at 70 degrees from A, C was at 130 degrees from the same A. To make sense out of this, again, here is a small diagram. I can still call them as 1, 2, 3, representing A, B, and C. It's still the same thing, but you can still go back to there. So mass 1 at R1, 0 degrees. Mass 2, this one, 70. The third one, 130. And the angles are neat like that because as we start the solving for the same, this is how we are going to use them. So here, resolving in the horizontal axis. Now, what I've put here is that first, it's just a clue to show us how we are going to be resolving this. So we have MR cos theta. So we have M1 R1 cos theta. Not really M1 R1, but just MR cos theta. Because there will be M1 R1, M2 R2, just like that. No need to put the numbers because there is mass 1, 2, and 3. From here, what we are saying is that mass number 1, it is 5 kg multiplied by its radial distance, which is how much? In this case, it's 120, 0.12, and the angle for mass 1 is 0. Leave it in brackets, then get to the second one, where the mass is 7 kg multiplied by 0.105 by 70, which is the angle from the center. And the third one we're told was at a radial distance or radius of 0.075. The mass was 12 kg and the angle was 130 degrees. So that gives us those 3. This, what you are seeing here, you can enter it in your calculator just like that, and it gives you that number. Or you may decide to enter one by one. The first set, you get the answer. The second one, get the answer. The third one, and then you add them up. The result should be 0.2725 kilogram meter, because you're multiplying mass by radius. So that's why it's ending up as kg meter. Let's do the same for the vertical axis. The same thing we did up there, but this time where there was cos, we introduced sine. And we continue like that. 5 cos 5 by 0.12, here we have sine 0, the other one sine 70, the last one sine 30. The rest of the information remains the same. So what happens to this? Your V will end up being 0.138. What is our imbalance? Our imbalance or out of balance is simply, we now introduce Pythagoras theorem for the two. So we say R, which is M4 R4, is equal to V squared added to H squared or H squared. So let's now substitute. So you have 1.38 squared plus 0.2725 squared. And from there, you have the answer comes out as 1.407. Now, here we are looking for mass 4. So if you take what we wrote here, we're saying that this is M4R4, which is in kg meter. So M4R4, can you please tell us what R4? The radial distance for the fourth mass is going to be how much? We were given already that this radial distance for the fourth mass, the other one that is needed to restore balance, is supposed to be positioned at 0.15. So that's why we say, let's divide by 0.15. And the answer is 9.38 kg. This is what you need to create balance for this particular system. This is the mass that you require. Now, the other part that was coming from this that was required is, can you tell us what the out of balance force is? How much force is going to come from this imbalance, so that we also know how much problems or trouble we're causing to the system? Perhaps the bearing may start overheating, or that wheel will start wobbling until we reach a point where the components are so worn that you have to now go and start replacing them. So here, we go back to the force, which is the centrifugal force, because this is a rotating member. And the value for omega was provided, which was 15.0796. It has to be given. This is the angular velocity. If it's given in radians, rather revolutions per minute, always remember to convert to the SI unit, which is radians per second. So what you see there is already converted in radians per second. So the replacement looks like a bit unfair, because M4R4 as a set, as a pair, can be checked here. It's 1.407. So there you have it, 1.407 multiplied by omega squared, and our omega is 15.0796. So then the answer is a force of 319.944 newtons. Now, the last part on this question was asking for the angle. The angle of the fourth mass from A, from 0. So that's where we introduce tan inverse. So tan inverse of V over H, tan inverse of V, check your V. Our V was simply 1.38, and our H was 0.2725. Now, tan is a very special one. Tan, you can even say tan inverse of 20, tan inverse of 1,000. Tan. Bigger numbers are accommodated, unlike sine and cos, where things are different. All of them have to be 1 or below 1. So what is tan inverse of 1.38 divided by 0.2735? Of course, you can always get one value from here before you go to the tan inverse. It still ends up with the same thing. The answer we have is 78.83 degrees. Or, because this is trig, the way the angles behave, they always come in sets. So this is in the first quadrant. All ASTC, all angles in the first quadrant are positive. In the second quadrant, it's only sine. The third quadrant, that's where tan is positioned. So let's get the equivalent in the third quadrant for this one. What do we do? You take the same 78.83 and add it to 180. So what you get after that is 258.83 degrees. That is the angle. Now, here's where you have to be a bit careful. This is not basically mathematical, not at all. I'm not entirely, but that's where we're starting from. From the mathematics, we have these two answers. Now let's go back to our technology, the way things happen in the workshop, the way things happen the mechanics of machines way. So here I have my three masses. I know mass 1 is here, mass 2 is there, and mass 3 was somewhere. Just here. I have mass 1, mass 2, and mass 3. According to the answer, I can put mass 4 here on top. But naturally, is that wheel going to balance? Mathematically, it will be okay. But if I run this wheel at the same speed, it will start wobbling, it will start making noise, it will start vibrating because it's not balanced. This is a kind of wheel, because it's very heavy on one side, when I give it a small push, it will always come to rest with this position, this lower part, the upper part with between M2 and M3 always coming to the lowest position. So then what? Let's pick it. We can either put it on top or below. So looking at the way the numbers are, it tells us that this should be positioned below there. And hence, the correct answer that we should pick for the 2 is this one here. If you go back to the wheel balancing machines, it will indicate to you where you're supposed to put that lead weight or that weight, and hence, this is where it is going to settle. And this is one of those, when the machine starts giving false errors, you can always do a quick test and recalibrate that machine, and you will know that this is going on well or things are not running fine. All right, let's meet again in the last parts of the, I've just handled the first 3 questions. So now I'll pick up the last, it should be almost the last 5, so that we proceed from there. As usual, this is your revision package. Should you feel like you need to clarify something, please drop a comment or drop that question in the comment, then I'll be able to respond.